Hi everyone. Right, I'm Dr. Sophia. Today we are going to look into the first method for the analysis to analyze indeterminate structures in our theory of structure subject that we call the slope deflection method. Right, so if we look into our course outlines that we have already briefed previously, the last topic that I have already prepared a video for you. It's regarding the introduction to structures. And in that video, you have also already understood the different types of structures like beams, truss, and frames, and the type of load like point load, uniform distributed load, and moment. And also we have covered on the stability and determinacy. You have been briefed the type of structures which is stable or not stable, and the type of structures which is statically determinate or statically indeterminate, and how to also calculate the degree of indeterminacy of the structures. So as mentioned in this course, we are going to study different methods in order to analyze statically indeterminate truss, beams, and frame. And we have different types of method that we can use to analyze this type of structure. And the first one is the slope deflection method. For this course, our syllabus will cover slope deflection method for beams and frame. And for beams, we are going to look into two types of condition. The first one is when the beam has no settlement, and the second one when the beam has settlement. So for this video, I'm going to cover the slope deflection method for beam when there is no settlement and when there is settlement. As mentioned, another video will be prepared for you for the shear force and bending moment diagram, in which it will be separated from this video, because for the preparation of shear force and bending moment diagram, since the method and concept is going to be similar for every other methods, then you can always refer to that video in order for you to refer back and to review how to prepare the shear force and bending moment diagram. So for this recording, we are going to cover the method of slope deflection method for beam without settlement and with settlement. And for the preparation of the shear force and bending moment diagram, you have to refer to another video, okay? Now, if you look into this continuous beam, I have a continuous beam with three spans. One span AB, another span BC, and another one more span. The third one is CD. And we have a pin support for all point in point A, B, C, and D. It is supported with pin support. And I have also one point load over here in between of span B and C. So if you can see here, since it is a pin support, it will have one reaction on the vertical reaction here, and also you have horizontal reaction over here. So I put here as the vertical reaction at support A and horizontal reaction as support A. Similarly, since B is a pin support, so you have another two reaction, horizontal and vertical, and similarly for point C, you have another two reaction, and for point D, you have another two reaction. So if you calculate it, for this continuous beam, I have 8 reactions in total, and since there is no internal or external pin, so therefore my C is equal to 0, so C plus 3 is equal to 3. And if I compare this value, I will have R bigger than C plus 3. So this is going to be classified as indeterminate beam. So basically it is statically indeterminate. I couldn't use the simple equilibrium equation in order to solve or analyze this beam. So the degree of indeterminacy of this beam is simply 8 minus 3 is going to be 5. So I have an extra 5 reaction that I couldn't solve it using the static equilibrium that I have already learned before this. So I will use a slope deflection method in order to analyze this kind of structure. And for the slope deflection method, the thing that you need to understand, the first thing is about the end moments. Okay. Now, in general, there are two end moments acting on a member. If I cut a member near the support, there'll be moment acting at each end. So if I have member, for example, member A and member B, okay, so for this one, member AB, and if I cut this member near to the support over here, then I will have an end moment acting on this part of my structures, okay, and another end moment acting at the end part of B support. So for one member, if I cut it, I will have two end moments acting for one particular member. Now, if I look into this diagram, let me just... Sorry, okay. All right, if I look into this diagram, if I have this continuous beam, like the one that I have already shown you before, it is continuous beam A, B, C, and D. And if I cut member AB, member BC, and member CD, I will have end moment acting on end A, another end moment acting at point at the end of B. So for this end moment at the beginning, the moment is assumed to be positive. So for positive moment, the direction is clockwise direction. Okay. So if I cut a member AB, it will be something like this. And for the end of A, I will have end moment. I name it as moment AB. So it is acting on the clockwise direction. Similarly, at end B, I will have another end moment acting, and it is also, I assume, to be positive. So it is a clockwise direction, MBA. So please be careful about the notation that I use here. For the part which is at the end of A, it is going to be moment AB. For the part from B to A, it's going to moment BA. Okay. Similarly to member BC, if I cut them in this direction and this direction, I will have moment BC acting at the end of point B and moment CB acting at the end of C. And if I cut member CD at this point of direction, I will have moment CD at the end of C support and moment DC at the end of D support. So all I assume to be a positive moment, so it is all in the clockwise direction. And using slope deflection method, we need to calculate all these moments to obtain the slope deflection equation. So this is the first steps. This is the first step that you have to do for the slope deflection method. You wanted to calculate all these end moments. You want to calculate MAB, MBA, MBC, MCB, MCD, and MDC. After you have calculated all these moments, then you can go to the next stage. So how you can calculate all these moments? Okay. Now we will see an example of one span. Then from this one span, you can see how this moment can be derived and how the equation can be simplified. And from the simplified equation, you can use it to the other span as well. So we take span BC as the example before we proceed to the other span. Okay. Now for this one end moment, like for example MBC and MCB, there are three types of moment acting at each end. So for one end, there are going to be three types of moment acting to it. The first one is moment due to member rotation, what we call the MMR, moment due to member rotation. The second one, moment due to support settlement. So MSS, moment due to support settlement. And another last one is the fixed end moment, fixed end moment. Now, if you wanted to determine what is the end moment of MBC or MCB, you need to calculate all these three types of moment for any end moment. Okay, so in order for me to calculate the end moment at BC, I need to calculate what is the member and what is the moment due to member rotation at BC, moment due to support settlement at BC, and fixed end moment for BC. And if I want to calculate the end moment for CB, again I have to calculate 1, 2, 3 for the CB. Okay, so we will look one by one. The first one, we will see about the moment due to member rotation. Now, what is the moment due to member rotation? It is if I have a member of BC over here and BC rotated on this direction, okay? If BC rotated on this direction like this one, so moment due to member rotation will try to push back this member back to the original position. So if originally I have my beam in this direction and it rotated to this angle, so in other words, the angle of rotation is counterclockwise. So the moment due to member rotation is going to try to push back this member to its original position. So in other words, I will have a moment due to member rotation in clockwise direction. So this is what we call the moment due to member rotation. The moment that is trying to push back your structure to its original position when it rotated. Okay. Similarly, at the end of C, since the member rotated on this direction, so in other words, the member rotated counterclockwise, I will have another, I will have a moment due to member rotation in this direction. Okay, so if the rotation is counterclockwise, I will have a moment due to member rotation clockwise direction in order to push back this member back to the original position. Okay. What is the equation to calculate moment due to member rotation? If I want to calculate MMR for BC, okay, the equation is 2EI over L times 2 theta B plus theta C. What is theta B? Theta B is this one. Okay, theta B on the end of B, and theta C is near to the support C. So keep this equation. MMR BC equal to 2EI over L times 2 theta B plus theta C. Now, if I want to calculate moment due to support settlement, what is the moment due to support settlement? It only happens if any part of the support of your beam has settlement. If there is no settlement, then this part you can ignore it. But if in the condition of your beam there is a settlement, then you have to include this equation. Okay, for example, if I have my member BC and it is given that for any reason the support C settled with a number of settlement of like delta, and it is the settlement is downward like this one. So in other words, my beam is going to settle in the direction of a clockwise direction, right? So if it is the settlement is a clockwise direction, it is considered to be a positive value for my delta. So moment due to support settlement is actually the moment that try to push back your structure back to the original position when settlement happened. So if your settlement happened on the clockwise direction, moment due to support settlement is going to try to push back your structure back to the original position. So the direction is going to be opposite the settlement. So this is what we call the MSS BC. Okay, so at the end of CB, again, you will have the settlement on this direction. So similarly, if it is clockwise direction and your moment due to support settlement is going to be on the opposite direction, that is the counterclockwise direction. Okay, it's like something like this. Now the equation in order for you to use to calculate the moment due to support settlement is this one: negative 6 EI delta over L square. So EI is going to be depending on the material properties of your structures, and delta is how much settlement happens for that particular support. So normally it is going to be given like, okay, support C settle 20, for example, millimeter downward. Now, if the settlement is positive, is a clockwise direction, so you can take the delta value to be positive. But if the settlement is like causing the movement of the member to be counterclockwise, then it is going to be a negative delta value. L is the length of your member, so that is the length of your BC. Now, this is the equation for the moment due to support settlement. The third one is what we call the fixed end moment. And this fixed end moment depends on the load of the member. If you can see here, the first two, it doesn't depend on the load of the member. So it is only depending on the material properties of your member, EI, the length of your member, and also the theta B or theta C, depending on the angle of the rotation. Similarly, of this one, only for the fixed end moment, it depends on the load on the member. So if, for example, I have a BC with the point load in the middle of span BC, since for the fixed end moment there is no deflection at support because we assume it is to be the fixed support, so there is no angle of rotation near to the support. The angle of rotation is going to be few distance away from the support. So if the rotation, if the deflection of my member due to this point load is going to be in this direction, okay, in other words, it's going to be clockwise direction over here. The fixed end moment, the direction of the fixed end moment is going to be opposite direction of the member rotation. So meaning if my member has this deflection of the clockwise direction, then my fixed end moment is going to try to push it back to the original position. So I will have a counterclockwise moment. Similarly, on this angle, if my rotation is counterclockwise, then my fixed end moment is going to be in the clockwise direction because it tries to push back the member to the original position. So I have in here to be negative and in here to be positive. Be very careful in terms of the direction because you need to put exactly a negative or positive in your calculation. Otherwise, if you did not put the notation over here based on the direction of the fixed end moment, then your calculation is going to be wrong. Okay. Now I have already calculated, I have already derived the equation for the end of BC, that is the moment due to member rotation of BC, moment due to support settlement of BC, and also the fixed end moment of BC. And I can just use this equation that I have already here, okay, MMRBC equal to 2EI over L times 2 theta B plus theta C. So this one is due to member rotation, and I have also due to support settlement negative 6 EI times delta over L square, and also I will have the fixed end moment over here, over here for BC. So I'll just put it in my equation. So this is the first one, that is the moment due to member rotation of BC, and I have another one due to support settlement of BC and the fixed end moment of BC. Okay, so for these two, I can simplify the equation until it goes to this one. Okay. So I keep first FEMBC because FEMBC is depending on the load which is imposed to the span of BC. And for this one, normally for the test and exam, you will be given a list of equation in order for you to see what is the equation that you can use to determine what, the value of FEMBC or FEMCB, depending on the condition of your loading. Now you have already solved the end moment of BC based on the equation. You have already derived the equation for moment at the end moment BC. Now this is the time when you have to look back at the other end in order to determine what is the moment for the end moment of CB. So for moment of CB, it is the again you have to include the three types of moment: the moment due to moment rotation, moment due to support settlement, and moment the fixed end moment. All is for CB right now. Okay, MMR CB, MSS CB, and FEM CB. Now, similarly, as what we have already looked for the MMR-BC, for MMR-CB, moment due to the member rotation at the end of CB, since the direction of the member rotated counterclockwise, okay, because this is the original position of the beam, and it rotated counterclockwise with the delta of delta C with the theta C. So the moment due to member rotation is going to try to push back the member to the original position. So MMRCB is going to be in the clockwise direction. So clockwise direction is going to be positive. Okay, so the same equation, you will have 2EI over L, but be very careful in here because you are from the end of CB, it will be 2 theta C plus theta B. Previously, you have MRBC, you have everything like this, but in the end, you will have 2 theta B plus theta C. However, for CB, you will have 2 theta C plus theta B. Okay, so it's different only on this part. Now, moment due to support settlement of CB is similarly with the previous one. You have this equation, and the only difference is that you need to be very careful with the theta, with the delta. Okay, right. So this one, I think it has a mistake because if this is the clockwise, this is also the clockwise direction. Okay, clockwise direction, and this one should be counterclockwise. So if your settlement is basically in the clockwise direction, so your delta is going to be positive, and the direction of your MSS is going to be opposite direction from your rotation due to the settlement. So if your settlement is clockwise, then your moment due to support settlement is going to be counterclockwise. Right, so this one also you keep in your list. And for the FEMCB, as mentioned, you can just use the formula that is given to you. So if I put all the values that I have from here for the CB, 2EIL to theta C plus theta B, I take this equation and this equation, so I just put it in here. So this is the value number 1 for the moment due to support settlement, and this is the fixed end moment for CB. Now if I make this equation simplified, for end moment of CB, I will have 2EI over L times 2 theta C times theta B minus 3 delta over L, and then I times with the fixed end moment of CB. So if you can see the pattern of this equation is the same, only the first one is going to be different. Okay, so if you are looking for end moment of CB, the only thing that you have to change here is 2 theta C plus theta B. Okay, the first one is C, so it's going to be 2 theta C plus theta B. Now you can see here when the time of end moment of BC, if it is BC, So it's going to be 2 theta B plus theta C. Now this is always the same. You only have to be careful with the notation of your delta. And this one, FEM, is going to be depending on the load condition that you will be given during your the example or the question. Okay, so this equation, you can also use it for different span of your beam. It is only the difference between if, for example, I am looking at the moment and moment of AB, then I will have to use 2 EI over L, then 2 theta A, okay, plus theta B. And if I want to have n moment of BA, then I will have here all the equation is the same, but 2 theta B plus theta A, and the others also same. And this one is depending on the loading between on the span of BA, right? So this is the time. This is what I meant just now. For span AB and span CD, you can always use the same equation that you already have derived for the member moment due to member rotation, moment due to support settlement for the span AB. So just look into here. N moment of AB is going to be 2 theta A plus theta B. Minus 3 delta over L plus FEM AB. If it is n moment of BA, so you will have 2 theta B plus theta A. Everything is the same. Okay, so all these are the same. All these are the same. And this one depends on the loading condition between these two points. Only this one is going to be depending on the end part over here. Okay, so 2 theta B when it is from B end, and 2 theta C when you're looking at the C end, 2 theta D when it is for the end moment from D end. Okay, now in order for you to understand better about the equation and how you're going to use it, because the only difference for the slope deflection method is this n moment equation. So this is the equation that you need to derive, and after you have derived this equation using the slope deflection method, then the remaining of the procedure is going to be similar with what you have already learned in your mechanic of material. There is no new equation or new method that you need to understand. It's only the continuation of what you have already learned. So once you get to this point correctly, then the others is going to be very straightforward for you. Okay, in order for us to see the method, in order for us to see the example of using this equation, we will see one condition of beam. Okay, one example of slope deflection method. For this one, slope deflection method, the condition is the beam, there is no settlement on the beam. Okay, first we look into the condition where there is no settlement. So for this beam, if you can see here, it is the continuous beam, and I have a cantilever end at point A. It is a cantilever in which I have a point load of 5 kilonewton acting on point A, and hold on a second. Okay, and for point B, it is supported by pin support, and for point C also it is supported with the pin, and for point D it is a fixed end. There is another point load between span C and D. In the middle span, I have another 30 kilonewton, and between in the span B and C, I have a uniform distributed load of 10 kilonewton per meter. The material properties for this beam in each span is the same. So I have EI for span AB, BC also EI, and CD also EI. Be very careful when the material properties of each span is not similar. So for example, if I have in here to be 2 EI, in my equation of n moment AB, in moment AB, I have to also continue with 2 EI. So in other words, if I have like over here for example 2 EI of span AB, okay, in here instead of 2 EI over L, I have to put 2 times 2 EI. Okay, so be very careful on this one. This EI is referring to your span. So if you have 2 EI over here, you have to put 2 times 2 EI. And if I have 3 EI for span B and C, so for B and C, I have to put the equation. For example, I put here. This way you can see. If I have 3 EI for span C and D, so for span C and D, the end moment equation will be 2 times 3 EI. Okay, instead of EI over here. So be very careful if it is not the same. But if it is the same, like in our equation in here, so it is a little bit straightforward for you. Now, once I get this type of condition of my beam to solve, I need to see what is the rotation of or the deflection mode of my beam due to the loading that is being imposed to my structures. So if I have AB as a cantilever and I have a point load at the end of A, so definitely I will know that the direction of rotation of the deflection of my beam is going to be something like this, right? Because if I have my beam straight and I have a point and one point load at the end of A, so my beam is going to be deflected this way. In other words, it's going to be deflected using this line. Okay. About the span BC, if I loaded my span BC with a uniform distributed load like this, then the deflection of my beam is going to be this way. Okay, it will deflect it this way. In other words, it's going to follow this line. And if I have my span DC SCD with one point load in the middle of the span, definitely my span also is going to be deflected in this direction. So with this predicted or deflection line, I can now understand what is the angle of rotation for my beam. So for this one, for the span AB, since the deflection is following this line, so my theta B, the angle of rotation is going to be the counterclockwise. And about span BC, I need to determine what is the theta B for span BC. Okay, so remember you have two theta B in here. One theta B is for span BA and another one theta B also for span BC. And for span CD, I have one theta C. And for span CB, I have another one theta C. So for this angle of rotation, since my beam is deflected in this direction, so my theta B is going to be clockwise direction. My theta C for span BC is going to be counterclockwise, and for span CD, my theta C is going to be clockwise direction. Since this is a fixed end, so there is no angle of rotation at the end of D, because this is a fixed end. So fixed end is going to be theta D equal to 0. Only a few distance away from D, you will have some angle of rotation, but near to the support, you will have theta D equal to 0. Now, I already knew that theta D is going to be 0, but I don't know what is the amount of theta C here and theta B here. So I need to determine what is theta C and theta B first. So if you can see, the direction of my rotation of theta B is this counterclockwise. So definitely you will know that I will have my end moment at this end to be counterclockwise of this one, meaning if this is the deflection of my beam, the end moment is going to try to push it in this direction. Okay, so I will have that direction later. We will see when we cut our member into the part by part. Now I will look first for member AB. So for member AB, for the cantilever, if I have for this cantilever over here and the deflection is counterclockwise, so I will have MBA to be in the clockwise direction. Okay, that I have already said to you here. Since this is counterclockwise, this moment tries to push it back to the original position, so I will have the clockwise direction. So due to this clockwise direction, I can easily calculate it. So MBA is going to be positive because this is the clockwise direction. This is the point load 5 times the moment arm. Moment arm is 2, so I will have 5 times 2 is going to be 10 kilonewton meter. So I will have my moment BA to be the 10 kilonewton meter, and this is the positive direction because it is clockwise direction. Now I keep this equation to be the value to be the first equation. Now I look into my member BC. So for member BC, what I have is like if I cut it, I will have it to be this way. I have point B, I have point C, and I have the rotation, the deflection of my beam to follow this line, and the angle of rotation, my theta B, is the clockwise direction. So I will have my fixed end moment to push it back to the original position is going to be counterclockwise, and for theta C is going to be in the counterclockwise direction. So I will have FEM CB to be in the counterclockwise, to be clockwise direction. And since I have 10 kilonewton meter of uniform distributed load, my FEM, my fixed end moment equation, I can use WL square over 12. So this is the equation I can use for FEM since it is the uniform distributed load. Now, in order for me to calculate what is the moment, the end moment for my BC, I can use the equation that I already have derived before. So we have 2EI over L times 2 theta B, because this is B, 2 theta B plus theta C minus 3 delta over L plus FEMBC. So since in this example there is no settlement, then I can always cancel out this one to be 0 because there is no settlement. And 2EI, L is 4 meter, so L is 4 meter. 2 theta B plus theta C. I do not know what is the value of my theta B and theta C, so I keep it as it is. And for FEMBC, since this is counterclockwise direction, so I have to put it as negative. Okay, so be very careful since this is counterclockwise, so this is why it is negative here. W is 10. Okay, the uniform distributed is 10, so I have 10. L, the length of the span is 4, so I have 4 minus 12. This one is square. So I solve this equation. I will have it to be EI theta B plus EI theta C over 2 minus 13.33. I keep this equation as number 2. Now I go to the other part of my beam. So this is the end moment from CB direction. Okay, end moment of CB. So similarly, I have this equation 2EI over L. So since it is CB, so I have 2 theta C plus theta B. Since there is no settlement, so I can cancel out this one to be 0 plus FEMCB. So FEMCB, since this the angle of rotation of C is counterclockwise, so I will have FEM to be clockwise direction. This is why it is positive. Okay, so this is positive. Now the value is WL square over 12. So W is 10, L is 4 square over 12, and I just insert the equation over here. 2ei over L. L is the length of the span, and I have 2 theta c plus theta b. I simplified this equation. I will have ei theta c plus ei theta b over 2 plus 13.33, and I keep this equation as equation number 3. Now I have already solved member AB and member BC. So I have one more member to solve, that is the member CD. So if you look into our support for member CD, I have a pin support and a fixed support over here, and I loaded it with one point load at the midspan of CD. So due to this point load at midspan pointing downward, the deflection of my beam is following this angle. Okay, this line. So in other words, for theta C is going to be clockwise direction, so my FEM CD is going to be counterclockwise. Similarly, for this angle, I will have FEM DC on the clockwise direction, because it tries to push back the member to the original position. Now delta D is going to be 0 because this is a fixed end, and theta C. So theta D is 0 and theta C, I do not know how much is the value, so I just need to put it to be theta C. And for a point load, when it is acting on the midspan, for a fixed end moment of DC of CD, I can use this equation, and from the fixed end moment of DC, I can use this direction. So negative, because this is a counterclockwise direction, and DC positive because it is the clockwise direction. So P is the point load, A is the distance between C to the point load. So this is A and this is B. For FEMCD, you use this equation, and for FEMDC, you use this equation. So this is A and this is B. This is L. You just have to put in all the value, and you will get what is the fixed end moment value. In order to get the end moment for CD, I use this equation similarly, like I have already derived it, 2ei over L. Since this is C, so 2 theta C plus theta D. There is no settlement, so I cancel out this one, plus fixed end moment at the CD. Now, if you look into this equation, it goes to 2ei over L. L is the length of the span, 2 theta C plus theta D. However, since this is a fixed end and there is no rotation near to the support or fixed support, so I can cancel out theta D as well to be 0. Okay, so plus FEMCD. FEMCD is counterclockwise. This is why I got it to be negative. Okay, so the negative in here, 30 is the point load. This one A, B, L. So I just put in all the equation over here, and if I solve it, I will have EI theta C minus 15. I put it as equation 4, and similarly I solve it for the end moment of DC, 2ei over L times 2 theta D, okay, because this is D, plus theta C minus 3 delta over L plus FEMDC. FEMDC is clockwise direction, so I have it positive over here, and there is no settlement, so this is 0, and there is no angle of rotation due to this fixed support, so this is 0. And if I solve this equation, I can make it simplified as equation number 5. Okay, now you have already derived the equation in order to determine what is the end moment for each end of the member that you have already cut. So you have this one, MBA. For this direction, A direction, it is, since it is cantilever, so you don't have any moment. So you have MBA, you have MBC, MCB, and also MCD, MDC. So, however, this value is all with theta. okay, with theta, in which you don't know what is theta, so you cannot determine the final value of your end moment before you determine the value of your theta b and theta c. Okay, so because all you left here is theta b, theta c, theta c, theta b. So you need first to calculate theta b and theta c. Okay, calculate theta b and theta c first before you can get what is the value of your end moment. How you can calculate your theta b and theta c? It is using the equilibrium concept because moment acting at support is always in equilibrium. What it means is that if you have a support of pin support at B, the moment acting on this support is going to be total moment is going to be 0. Similarly, for a moment at the pin support over here, the total moment is going to be 0. So moment acting at support is always going to be 0. So you use this concept in order for you to solve what is the theta B and theta C value for your beam. Now MBA, we have already calculated it because in here you can see, okay, MBA is positive 10 kilonewton meter. So this is why I put positive, it is clockwise direction, 10 kilonewton meter. Now, if at the end of your member you have a positive moment of 10 kilonewton meter, so our positive MBA, at the end of this connection between the member and the support, you will have another moment which is acting at the opposite direction but similar value. So in other words, if I have at this point counter a positive moment MBA, I will have in here a negative value of the same moment MBA. So in here, clockwise direction, in here at the other end is the negative direction. Okay, so similarly we have already come up with the equation of member of end moment for member BC and end moment of member CD, but we don't know the final value and we assume it to be positive, right? So this is why for member BC, okay, so for member BC over here, MBC, MCB, we assume it to be positive, and this is the equation, so it is here. So this is the value of MCB, positive direction, clockwise, and this is another clockwise direction of MCB, the one that we have already calculated before. So similarly, for member CD, you have a positive moment of MCD, and you assume it to be also clockwise direction for MDC. So MCD is this one. MDC is this one. So you have this equation and this equation for DC. So you have actually determined this value and this value in terms of the equation which contain theta C and theta B. In order to maintain the equilibrium of your system, if you have clockwise moment at this end, you will have to balance it with another moment MVC, the same value but different but opposite direction. So this is why you have in here MCB but counterclockwise. If you have here clockwise direction MCB, so you will have MCB counterclockwise. If you have in here clockwise direction MCD, you will have here counterclockwise direction MCD. And if you have in here end moment of DC clockwise direction, you will have to balance it with another moment DC counterclockwise. Now you knew this value, you knew this value. So you can always know this value because you just change the direction of it for this support and for this support and for this support. So in order to maintain equilibrium, our theory is that moment acting in the support has to be total to 0, because in order to maintain equilibrium, so you take this one, okay? So this MBA plus MBC should be total equal to 0, and you take this one, should be total to 0, and you take this one, you balance this, right, with the end moment of the fixed end moment over here. Okay, so we can solve this one first. MBA plus MBC equal to 0. Now, for the equilibrium of moment at B, I will have MBA plus MBC equal to 0. Okay, so MBA, I just take the value over here, MBA, this one, MBA, positive 10 kilonewton meter, and MBC to be this one. Okay, so MBA plus MBC equal to 0. Now I take the equation that it's a very straightforward equation that you already learned how to solve. So 10 plus this one equal to 0. Now I just solve this equation for the linear equation over here, and I will have another equation, so I put it as 6. Now the second equilibrium for the support is at for equilibrium of moment at support C. Now for support C, I will have MCB plus MCD should be equal to 0. So this is why MCB plus MCD equal to 0. So I just use this equation that I have already derived, MCB. Okay, so this equation number 3 plus MDC, this is equation number 5, should be equal to 0. Okay, so this is the equation that I have already derived, should be equal to 0. And if I solve this equation, I will have another new equation to be equation 7. Now, please be careful. In some cases, they will say that there is external moment being a point or being imposed at support C. For example, there is additional of 10 kilonewton meter clockwise moment being imposed at a point at support C. So when this is the case, you should include this negative moment in order for you to get the equilibrium at point C. If there is no additional moment from outside, then you can always solve it directly as it is. Okay, so I have new equation 6 and 7. It is just a simple solution for it. Then in the end, you will have what is the value of your EI theta B, EI theta C. And with this value EI theta B and EI theta C, substitute it to the equation that you have all this while, then you will have all the amount of end moment that you have already derived the equation. Now, if I take this value over here, okay, and I substitute it to the equation 2 to 5 that I have already derived before, I'm able to determine what is the end moment value for BC, end moment value for CB, end moment CD, and end moment DC. So this is the value that I have already determined. And if you can see here, I determined for my end moment BC to be negative 10. And this is positive 15, negative 15, and positive 15. So this is the time when I understood that the positive direction that I assumed before is not correct. So I have to update the direction of my moment to be negative. So meaning, so for MBC, the direction of my moment should be counterclockwise. And this one is similar with the one that I assume. It is positive, so it is clockwise direction. And this one is negative, should be counterclockwise. And this one is positive, should be clockwise direction. This is the time when I have to update the direction of the moment based on the one that I have already calculated before. Now, from here, I just take this value and plot it back to my beam. So the first one that I have is positive 10 kilonewton meter for MBA. So this is the clockwise direction. And for BC, I have negative 10 kilonewton meter. So this is why for BC, it is counterclockwise, 10 kilonewton meter. And for CB, it is positive 15. So clockwise direction, 15. And for CD, negative 15. So negative 15 is counterclockwise 15. And for DC is positive 15. So clockwise direction 15. This is all that I have calculated based on my slope deflection method. This one, this one, this one, this one, and this one. So right now, if I wanted to draw my shear force and bending moment diagram, I need to know how much is the reaction on my support, right? So in order for me to get the reaction on my support, I assume, or I give the notation of B to be the RB, and on C I have RC, and on D I have the vertical reaction at D, and since this is a fixed end, I have another one to be MD, moment at D. Alright, so these are the support reaction that I need to determine in order for me to get my shear force and bending moment diagram. So now the next stage is for me to calculate support reaction RB, RC, RD, and MD. Okay, so this one, this, and this. After I have calculated my end moment, okay, so this is the end moment that I have already calculated. Now this is the time that I need to calculate my support reaction. How I can calculate my support reaction? First, I need to assume the direction of the reaction. So in here, I assume for each support, the direction is pointing upward to be positive. Okay, so I assume it's all to be upward positive. And once I get the real value of my support reaction, then only I will change the direction to be the S in the final value. To solve this, how I can get the value of my support reaction, I can solve it based on the reaction for the end support. Okay, so before I can get this, I need to solve one by one first. This one, and this one. Because if you see here, if I have this direction, I definitely need to balance it with another one over here. Okay, and in order for me to maintain the equilibrium, as what we said, at the end of the moment, there is another moment reacting on it, but different directions. So similarly, if I have, so for example, this is A, if I have pointing downward over here, then I need to have another support reaction, the reaction on the other end of my member. So I put it to be VAB. Okay, VAB over here. So I can calculate how much is this one. And in order to balance this VAB, I will have one reaction on this one. So this is VAB, similar value but different direction. And if I want to calculate the total in here, definitely I need to calculate how much is going to happen on this side. So I can assume this one, okay, to be VBC, and this one to be VCB. So for in order to balance this vertical direction of load on BC, there should be another vertical direction, VBC, but different direction. And for this one also, I will have another one here, VCB, and this one, I put it to be VCD, and this one, VDC. So in order to balance this VCD, I need to have a different direction of VCD. And in order to balance this one, I need to have another, this one, VDC. Okay, so it is very straightforward for you to calculate how much is VBC. Once you get how much is VBC, you just need to balance it at the other end, and you will have VBC over here. And in order for you to get what is the amount of RB, so RB is going to be the total of the, this one should be also equal to 0. Okay, the total of the reaction over here, vertical Fy, equal to 0. So you will have RB. And similarly, you can easily get RC, you can easily get RD. For the moment over here is very straightforward, because if you have at the end of CD 15 kilonewton meter, this is clockwise direction, so you will have over here counterclockwise direction. And definitely in order to balance this, you need to have another moment to be MD at the clockwise direction over here. So MD, you can easily get it, and this one also is very straightforward for you to get it. Now, once you know the concept, you can easily do the calculation very simple. So I put the sample of calculation over here also for your reference. To get support reaction for member AB, if I have a span AB in here with the vertical load pointing down on 5 kilonewton, and I have one moment over here, so I can easily get the loading over here, total Fy equal to 0, so I have -5, and this one is pointing upward, plus VBA equal to 0, so easily I can get VBA equal to 5 kilonewton and pointing upward, so meaning in the positive direction. So this one is going to be 5. So this one is going to be 5 kilonewton, sorry, is going to be 5, and this one pointing downward also is going to be 5. Now, for member BC, I have VBC and VCD. I assume it to be positive direction all together. And in order for me to get one of these, I choose total moment at C equal to 0. So since total moment of C equal to 0, I will have VBC. Okay, it is going this direction. So it's going to be clockwise direction. That is why it's positive. So for the moment arm times VBC, so for VBC, then I will have this one pointing downward because this is the uniform distributed load. So for this uniform distributed load, I will have at the midspan here, I'm acting in it. In order for it to reach C, it has to go this way. So it is going to be counterclockwise, okay? Counterclockwise, so this is why it's going to be negative. So negative 10 times 4, this is the total point load, 10 times 4, and the moment arm is going to be the mid distance, so it's going to be 4 divided by 2, so this is 2. I also have the moment, this one is negative because it is counterclockwise, 10, and this is another one, clockwise direction, positive, so this is where it comes minus 10 times 15, because this is the end moment at B and moment at C equal to 0. I solve this equation, I will have VBC to be 18.75, and this 18.75 has to be balanced. Okay, so if it is pointing upward, 18.75, pointing upward, so VBC pointing downward, 18.75. Okay, and for VCB, total Fy equal to 0, so I have positive going upward 18.75, and this one pointing downward 10 times 4 plus VCB because it's pointing upward, so I will have VCB equal to 21.25. VCB 21.25. VCB, so this one is 21.25. In order to balance it, I will have this one VCB that is 21.25. So right now, if you can see, if I have pointing downward 5, another pointing downward 18.75, definitely RB is going to be very easy for me. It's going to be RB is plus, going to be total equal to 5 times 18.75 equal to 23.75 kilonewton. So I have already the reaction for RB over here. Now the same method, I just need to solve this CD in order to get my C reaction. Of 15 kilonewton. So this one is just very simple. So I will have like this, I will have like this. This is the 30 kilonewton midspan, so I will have this 15, and this 15 over here. So in order for this one, I have 15, so this one is equal to 15. So RC equal to 21.25 times 15. So I will have this one. Okay, this is the time. 36.25. So I have 36.25 kilonewton for my RC. Now the same thing for VCD. So since this one is 15, you need to balance it with 15 kilonewton. So in order to balance this 15, you have RD equal to 15 kilonewton pointing upward. So you have already the support reaction of RB, RC, and RD. And this one, in order to balance it, is just you use the moment of VCD. If this one is clockwise direction, so it has to be balanced with the counterclockwise with 15 kilonewton meter. In order to balance this one, you will have another clockwise direction for the MD. So this is what MD, you will have positive 15 kilonewton meter. Okay. So MD positive 15 kilonewton meter. So now the moment you have determined all of your support reaction, MD also you will have 15 kilonewton meter. And this one RC you have 36.25, and RB you have this one. It is very straightforward right now. You can easily draw your shear force and bending moment diagram. Of course, before this, when you draw your shear force and bending moment diagram, you have different method for you to draw it. It is based on each one of your preference. Some of you might want to draw your shear force and bending moment diagram like span by span. Another one wants to draw it as a continuous one. The next video that I prepared for you for the shear force and bending moment diagram, you can refer to it. I have explained in detail how you can draw the shear force and bending moment diagram for both methods. Those of you who prefer part segment by segment or span by span, you can do this span by span. And those of you who prefer to do it like in a continuous beam, you can also do it whichever you prefer and whichever you feel comfortable for you. So please refer to this video, shear force and bending moment diagram video, in order for you to see how you can draw the shear force and bending moment diagram for this example. Okay, and this method of drawing shear force and bending moment diagram is going to be similar for other example as well, or for other condition. So this is why I separated the video in order for you to be able to refer it at any time you wanted to have a revision on how to draw your shear force and bending moment diagram. Okay, so for the example of for the condition of beam without settlement, this is the example of it, and the whole procedure of analyzing it using slope deflection method we have already covered in this session of explanation. Okay, and we will continue in order to see another one example. What is the method, or what is the differences for you to use this slope deflection method for beam with settlement? It is not a very difficult condition, because as I mentioned to you before, the only difference is like the delta, the equation of this one. Okay, so we have already looked into this equation over here. So it is the same procedure, the same method. The only difference is that this one, okay, and this one. The time when the beam has settlement, then you will have this part of the equation only, this part. And you have to be careful if the settlement is either it is positive or negative, because it's going to make a difference in this delta value. So you just have to use the same equation and just put the value of the settlement for that span, but be very careful with the value, whether it is millimeter or centimeter, because if your span is given in meter dimension, so and sometimes the settlement is given to you in millimeter or centimeter, then you have to convert it first before you can use the value in this delta, and you have to be very careful if it is positive or negative. Then you can just insert the value over here, the procedure of solving the equation, the procedure of determining the theta b, theta c, and also the procedure of getting the end moment using equilibrium of support is all going to be the same. There is no different. Only different is this part of the equation. Okay, so you can see it is very straightforward. Only this part is going to be added to your job, and the other one is all the same. In order for you to see better about the example and on how to use the equation positive or negative and things like this, we are going to do one example, and this example is also similar to the beam that we have already solved before. Only the one added is that I mentioned here the support C settled 20 millimeter downward. Okay, so if you can see here, it's the same beam. You have a continuous beam being on cantilever at A, supported with pin at B, supported with pin at C, and supported fixed end at D. And the condition of the loading also is the same: 5 kilonewton point load at the end of the cantilever, 10 kilonewton meter, uniform distributed load 30 kilonewton at the end of at the midspan of CD, and the span is 2 meter, 4 meter, and 4 meter over here, EI. So there is no difference. It's all completely the same, except that right now support C settled 20 millimeter downward. Okay, so with this settlement of point C with 20 millimeter downward, then your equation is going to be added in terms of the delta value. That's all. Now we are going to see how you are going to solve this problem just by adding this delta over here. Okay. Okay. So for this example, the only difference, as mentioned, is just the displacement, okay, or the settlement. And it is given, the settlement is at point C of 20 millimeter pointing downward, okay. So as mentioned before, the only thing that we are going to make a difference is the part of the equation which has the delta. And in this delta, you have to be very careful about the amount of the settlement and also the direction, whether it is positive or negative, because you're going to put it in this delta equation. And given here is support C settled 20 millimeter. Be careful, whatever the value that you have here is in meter, so this one is in millimeter. You have to convert it first to meter before you can use the value. Okay, some students make a very simple mistake. They just put 20 inside of this delta, so all the calculation is going to be completely wrong. And the second one is the positive or negative. So if you can see in here, for us, due to the settlement of point C, the only part which is going to be affected is span BC and span CD. The span AB, there is not going to be any changes because there is no settlement, and for B, so meaning whatever you have calculated for member AB is going to be similar. Okay, only the part for member BC and member CD is going to have any changes. And in order to see this the effect of the settlement, you need to first determine the orientation or the positive or negative sign of your delta. So for BC, how you going to look into it? So since support C is settled downward like this, so the deflection of your beam is following this line, right? So your beam is going to be deflected this way. And for this one, the angle of rotation due to the settlement at the end of BC is going to be clockwise direction. So similarly, if I cut it on this one, okay, so for this angle, it is also clockwise direction. However, if I cut it from this and this for the end moment, at the end of D, so it's going to have a counterclockwise direction, and towards the end of my span CD, it's also going to have a counterclockwise. So in other words, due to the settlement, I will have a positive delta because it is the clockwise, and this is also clockwise direction, so it's going to be positive for my end moment CD CB. However, for my end moment CD, since this is the counterclockwise, so it's going to be negative delta. And similarly for the end of D, since it is counterclockwise, it's going to be negative. So you keep this value for BC is going to be positive delta, negative delta, and negative delta. Then you just put it in your calculation. Okay, so for MBA, it is similar. Like you have already calculated, so it's 10 kilonewton meter. The only difference is going to be for moment BC. So for moment BC, the equation is going to be 2EI over L times 2 theta B plus theta C minus 3 delta over L plus FEMBC. So FEMBC, there is no difference. It's going to be all the same, like you have already calculated before, like I have already explained before. So this one is going to be all the same. Okay. This explanation is going to be the same. The only difference is that this delta over here. Okay, so before this we cancel out delta because there is no settlement, but since there is settlement in here, and for MBC, it is positive delta, so I put it to be positive 0.02 because this is 20 millimeters, so 0.02 meter. Okay, so delta positive delta positive 0.02, so positive 0.02. Everything you maintain, negative 3, everything you maintain, only you change on this part. Okay, positive 0.02, and you continue all the calculation to be the same. So that is MBC. So for MCB at the end of CB, still the angle of rotation due to the settlement is clockwise direction. So you will have positive delta. So this is why you have positive 0.02. Divided by 4, as in the equation, everything is going to be the same. Still the same, for MCD, from C to D, since this the angle of rotation is counterclockwise, okay, counterclockwise, so negative delta. Negative delta is negative 0.02. Just put in your equation negative 0.02. Only this one is different. Okay, so everything is similar. You will get it all correct. And for MDC, since the angle, due to this settlement, our beam deflected this way. In other words, the rotation is counterclockwise. So since it is counterclockwise, it's going to be negative delta. So negative delta, you put it here, negative delta, and it's going to be negative 0.02 for MDC. Everything is the same. After you have calculated all the equation, you need to calculate what is the amount and what is the value of theta B and theta C first. And theta D is still 0 because you have a fixed n. Then after you calculated this one, you will use the equilibrium of support to get this theta. And once you get this theta, you will get the equation of n moment BC, n moment CB, n moment CD, n moment DC. And once you get the end moment all together, you will use the equilibrium of forces at support to get the reaction of RB, RC, RD, and MD. And when you get this reaction, then it is very straightforward for you. You can draw the shear force and bending moment diagram. Okay, so I need you to continue with this example, the one with beam with settlement, in order for you to be familiarized on how to solve the equation, to review back on how to get the equilibrium of moment, equilibrium of reaction, and I need you to draw the shear force and bending moment diagram based on the method that I have explained to you in the video of shear force and bending moment diagram. Okay, so that would be your second assignment. I need you to give me the drawing of shear force and bending moment diagram for the beam with settlement. Of course, in your submission, you have to include all the steps again, and all the calculation until you get the reaction of the support, and from there you can draw the shear force and bending moment diagram. Okay, so complete the example and give me the full solution in your submission. That will be your assignment number 2. Okay, all right, so I will create also the detail about this assignment and also the submission due date in your e-learning. So good luck to all of you, and I hope you understand it very well, very clearly. If you have any question for the explanation and everything, you can ask me during our next lecture. Okay, so good luck and bye bye.
انضم معنا الآن واشترك بالقناة ليصلك كل جديد. YSAG، معا نحو مستقبل مشرق.